solutions are homogeneous mixtures, which means they usually look the same throughout, means things dissolve in each other. And solutions are the guys that have the AQ symbol next to them, the aqueous symbol. So AQ means aqueous, means it's a water environment. There is a difference between aqueous and L. L is liquid. How you make an aqueous guy? You take something like water, which is a pure liquid, and you mix it with something like sodium chloride, which is a solid. That sodium chloride will dissolve in the water, and it will make a sodium chloride solution that is aqueous. And again, so aqueous implies it's a solution and that it is a mixture of two things that dissolve in each other. It's a homogeneous mixture, which means everybody's going to mix nice and everything's going to look the same throughout, right? Again, a pure liquid is just by itself. So again, there is a difference between L and AQ. So let's talk a little bit about solutions and the different parts of it. Many reactions occur in an aqueous solution and an aqueous environment. And a solution itself, as I mentioned, is a homogeneous mixture. And it's actually made up of two parts. There is the solute, which is the smaller part of the solution. And there is the solvent, which is the larger part of the solution. Typically, your solute will dissolve in your solvent. So the example I just did where I took my water and I put some sodium chloride in it and it dissolved and it made a sodium chloride solution. Water, in this case, is my solvent. My sodium chloride is my solute. It's the stuff that will dissolve in it, basically. Together, they will make a sodium chloride solution. How do you know what the solute is when you have a solution? It's pretty simple. It is the name of the solution. So if I have a sodium chloride solution, sodium chloride is my solute, yeah? If I got a potassium chloride solution, potassium chloride is my solute. If I have a hydrochloric acid, hydrochloric acid is my solute. So whatever the name of the solution is the solute. I will say that a lot of times water is a solvent, but it is not a good solvent for everything. For ionic and things that are polar, water works really well. But for things that are non-polar, it does not work well at all. So 9 times out of 10, probably water is going to be your solvent, but it will not always be the solvent. So it does not always has to be the solvent. So here's copper 2 sulfate, the solid before you begin. That is our solute. Our water against our solvent, much larger. Give it a mixy, maybe a shaky, right? And those guys break apart. Those ions start floating around, right? By the way, this in solution is where we find ions, yeah? So when we have a sodium chloride solution, it's a strong electrolyte. It's basically all sodium ions floating around. It's all chloride ions floating around in that solution. So if you ever wondered where are ions, ions are in solution. They're floating around in the swimming pool, basically, yeah? Floating around in that part of it. Now, as I mentioned before, water is a really good solvent for a lot of things. There is this idea when we talk about things dissolving in other things known as like dissolves like. And what that means is if you take something that's ionic, it will be pretty soluble and mix really well with something that's polar. If you take something that is polar and you put it with something that is polar, they're going to mix okay. If you put something that is nonpolar with something that is nonpolar, it will also mix. So all these guys would be soluble in each other. They all will mix in each other basically, and everything will. It is only typically when you cross over from polar to nonpolar, that is very problematic. They're typically going to be insoluble in each other. They will not mix like oil and water. You can mix that all day. The oil and the water will eventually separate out from each other. The reason for that is, and when we talk about things being polar and nonpolar, we're talking about what we talked about with bonding, molecular polarity. The molecule is either polar or nonpolar. If you remember what that means is if something is polar molecule It means that they are not sharing the electrons equally overall the whole molecule. And what that really means is when you have a polar molecule, there is a positive side to that polar molecule and a negative side to that polar molecule. Like water. Water is a polar molecule. The hydrogen side is more positive. The oxygen side is more negative in water. And that allows it to interact really well with other polar molecules because pretty much how all molecules interact with each other is a basic interaction of opposites attract. So the positive side of one of those polar molecules will be attracted to the negative side of another, and they will mix really, really well together. That is also why something like water, which is a polar molecule, is really good for ionic compounds because ionic compounds have charges because they're really made up of ions. So when you drop something like sodium chloride into water, you get a sodium ion, you get a chloride ion. And what happens is the water molecule will surround the positive ion with its oxygen, which is negative, and help that sodium chloride dissolve in solution. Same thing will happen with the chloride. It's negatively charged. The hydrogen side of water, which is positive, will start to surround the chloride ions, right? And when you look at that and you take some salt or something in water, we help this process along by stirring, right? When you stir it, you throw a bunch of water molecules all over that ionic solid. The ionic solid to start with, it's just all clumped together basically, which is why you can see it, those positive and negative ions together. But when you stir it, you throw water molecules on there. You also add energy. That allows those water molecules, because there's so many of them, to pop those ions off basically and start surrounding those ions. There's so much water molecules when you dissolve something like salt, right? It looks like it disappears, right? And it does because you can't see it anymore because there's just so many water molecules surrounding those ions that it is not visible to you anymore. But it's still there, as you might see in this experiment this week, maybe, or maybe you've done before. You heat up a solution of sodium chloride, right? And you can't see any solid. When you heat it up, when we heat up something that has water, that's going to evaporate off all these water molecules, right? And you'll get rid of all those water molecules, and there'll be nothing in the way of those two ions sticking back together. And you will see the solid come back, right? And that's how we know it's actually a physical change when you do a solution, because nothing is lost. What we start with and what you end with is still there. You just can't see it. It looks different when it's dissolved in a solution type form. Any questions on that? By the way, nonpolar works really well because they both use what is known as dispersion forces, which are actually pretty weak forces. They basically both don't have charges, so they interact really well. That's why when you take something that's nonpolar and polar and put it together, they have a real problem, because nonpolar things, which are kind of neutral, wants to use these dispersion forces, which are these really weak, bad interactions. Something like water wants to use these polar forces, and those are not two of the same type of interactions. So they're not going to be able to interact well with one another for a long period of time. That's why they cannot maintain that interaction, like oil and vinegar salad dressing, right? You can shake it up, right? It mixes, but if you leave the bottle on the table, it eventually does what? Separates out, right? Because it cannot maintain that sort of mixture and those interactions over a long period of time. They can do it for a short period of time, but there's just no way to allow it to stay there. Any questions on that there? And here's a picture of what I was talking about. This is basically what something like sodium chloride looks like in a solid form, just all the ions stuck together in a very organized fashion. And again, when you throw your water on there and start stirring it, it's able to pluck off those ions. Eventually it will dissolve and not look like it's there. Here's another picture of that, and a third one in case you didn't like the first two. Same idea here. So let's talk a little bit about these examples of solubility in water. As I mentioned before, ionic compounds are good to go with water because they're able to do those opposite attraction. The water will just surround the positive ions. They'll surround the negative ions. They will help everything mix. They'll work themselves into the water mixture. But we also have non-ionic compounds like sugar and ethanol, which are also very soluble in water. And the reason for that is if you look at something like ethanol, it looks something like this. And if we look at something like water, it looks something like this. And water, as I mentioned before, is more negative on the oxygen, more positive on the hydrogen. How water interacts with itself and how molecules interact with one another is through what is known as an intermolecular force. And an intermolecular force that water uses with other water molecules is basically the positive side of one water molecule is attracted to the negative side of another. This is what is known as hydrogen bonding. All right, this way. Hydrogen bonding. Hydrogen bonding is a type of interaction which is known as a dipole-dipole interaction. You might also remember the word dipole. We saw it with polar molecules. They have dipole moments, yeah? So that's why it's called dipole-dipole interaction. But two water molecules, how they interact with one another is through hydrogen bonding. Hydrogen bonding has to occur between you. The only way you could do hydrogen bonding is you need a bond between hydrogen and an electronegative element like nitrogen, oxygen, or fluorine. So that hydrogen has to be directly attached to an oxygen, nitrogen, or fluorine, which it is in water. Clearly that hydrogen here is attached directly to the oxygen, so it's able to hydrogen bond. This hydrogen is directly attached to that oxygen, it's able to hydrogen bond. So when we look at ethanol, it actually has that exact same bond that you see in water. It has that OH group. So it has a negative and a positive. That's a polar bond, which when it hooks up with water, works really well because it could also hydrogen bond with water. So it's able to hydrogen bond with water the same way that water could hydrogen bond with somebody else. And that makes something like ethanol really, really soluble in water because it has the same type of interaction. Now, just to verify all these hydrogens here, can they hydrogen bond? The answer is no, because they are not directly attached to a nitrogen, oxygen, or fluorine, right? They are actually directly attached to a carbon. And that's actually not going to create a polar bond. It's a non-polar bond. So even though there's hydrogen present, it cannot always hydrogen bond. It has to be the hydrogen that is directly attached to a nitrogen, oxygen, or fluorine, like we see at the end there. Ethanol has two parts. It has a non-polar part, and it has a polar part up here in front. Sugar as well is also very soluble in water. Sugar is a little larger of a molecule, but it is littered with OH groups everywhere. So it has a lot of OH groups everywhere. And everywhere there's an OH group, it allows it to interact well with water. And it makes something like sugar quite soluble because of those OH groups. Okay, let's continue on then. We are talking again here about really solubility in water. And if something is soluble, again, it pretty much means that it mixes. It all comes together in a nice solution. If it's a solid, it will dissolve. Obviously, if it's two liquids and they're soluble, they'll mix and it'll all just look like one liquid, basically, if you put it together. As I mentioned before, something like ethanol or sugar are going to be really soluble because they do contain on them groups that allow them to interact well with water through this process of hydrogen bonding. And again, really, it's just sort of opposite attraction there between the hydrogen and, say, the oxygen there. So here's, again, a picture of that. This is actually methanol, which is like ethanol with one less carbon. But again, here you can see it also has the OH group. And again, going to be able to do the hydrogen bonding there with those water molecules. And it's going to be able to interact really well. Now, ethanol and methanol aren't super large molecules, which also helps to sort of interact. Remember that if you're going to dissolve something in water before you do that, you pretty much have to break apart all these water type molecules, right? And sort of replace them with whatever you're trying to dissolve in there. And again, if something's really, really big, it creates sort of a problem for that to happen. But if it's small and has a way to interact well with water, it's going to make it very, very soluble. Here's our ethanol example again, our hydrogen bonding there happening. Now, what about oil and water? Do they mix? They really do not. And oil is insoluble. The major sort of component of oil is basically a bunch of carbon to carbon bonds and carbons attached to hydrogens, basically. So it's carbons and hydrogens all the way across. And those are all nonpolar bonds. And as I mentioned before, what happens with oil, because it essentially is nonpolar, because all it's got going for it are these bonds here, it's not going to have any way to interact well, and it just kind of keeps going very long on each side because it's going to want to use again those dispersion forces, which are those relatively weak intermolecular forces. And water, again, is going to want to use basically hydrogen bonding to interact. And those are very, very different types of forces. And again, they're not going to be able to maintain that. What is a dispersion force and why is it so weak? It's so weak because basically, if you have two nonpolar molecules, they're basically neutral. So they can't really interact with each other until somebody gets some charges. So they have to rely upon something happening to them to give them a charge. So one thing that could happen to a nonpolar molecule is all their electrons, for example, may end up as they're moving around to be on the right-hand side of the molecule versus the left-hand side of the molecule as they're flying around. You get this big amount of electrons all heading to one side. The result of that is because of that unequal sort of electron flow, this nonpolar molecule, which normally doesn't have a charge, will now temporarily gain a charge. And if it's still sitting next to another nonpolar molecule, all the electrons in this guy's going to go, that's negative. I don't like that. I'm going to go this way. And all those guys' electrons are going to go to the opposite side of that molecule. So now on those two nonpolar molecules that didn't have charges, they will temporarily gain charges. And that's how that dispersion force is able to interact. It's temporarily because when those electrons come home from their vacation, they're not going to no longer have that charge and it's going to fall apart and make new interactions. And then those will fall apart and make new interactions and those will fall apart. So they're very, very temporary. And that is also why when you put something like water and something that's nonpolar together, something like a polar molecule can temporarily do that to a nonpolar molecule. So if that's a polar molecule, that's a nonpolar molecule, it could cause those electrons to kind of go the opposite way. And once again, you'll get this temporary sort of interaction between this polar and nonpolar molecule that they can interact with each other. But once again, as soon as they kind of move away from each other, that nonpolar's electrons are going to come back and they're not going to be able to maintain that. Kind of like how we just talked about at some point, everything will just separate out from each other. They're not able to maintain that interaction over the long period of time. So when we have something like oil, which is nonpolar, not going to be able to interact well with water, they are not going to be soluble in each other. The other problem with oil is it's super big usually. It's pretty long carbon chain, which means you're trying to park something into water, which is relatively small, and it doesn't fit really well. Again, like if you're trying to park a car in a garage, it's going to be fine, right? But if you try to put like a semi truck in the garage, you get some of it in there, but it's not going to fit just right, right? So it's kind of the same idea here. It's relatively big. It doesn't have good interaction with water, so it's going to make it very, very insoluble in this idea. Any questions on that there? That again brings up the idea of, as I mentioned earlier, of like dissolves like. Again, things that use the same type of intermolecular forces that they use with themselves will be able to use it with somebody else and interact well. Again, if you get two things that are using very different interactions, they will be insoluble in each other. Pretty much the main one of that is something that is polar and nonpolar, trying to put them together Not going to happen. But if you have polar and polar, you're going to be good. You have ionic and polar, you'll be good. And if you have nonpolar and nonpolar, you'll be good. But again, if you cross over polar and nonpolar, it's not going to work really well because they will not be able to interact with each other over a long period of time and keep that interaction going. Any questions on that there? So here's sugar, which is a relatively big molecule, but what the main advantage of it is, everywhere you can see it's littered with OH groups, and everywhere there's OH groups, it just increases the solubility of it in water. Here's pretty much what oil looks like, just a long old chain of carbons and hydrogens, non-polar all day on that one. And again, not going to be able to interact well with water. And that's typically what we do see, right? We see an oil layer, which is on top, and a sort of water layer on the bottom. And that always happens, by the way, even in experiments you do, you mix some things together. Top layer is always the sort of organic nonpolar layer. Bottom layer is the water layer. They separate out that way. Just like if you've seen an oil spill, right, in the ocean, the oil starts to float on top, right? You can see the oil floating on top. That's because it can't mix, right? And that's problematic. So let's talk a little bit about solubility. If one substance is going to dissolve in another, so if the solute is going to dissolve in the solvent, it's said to be soluble. So salt is soluble in water. When one substance does not dissolve in another, they are said to be insoluble in water, or insoluble in general. Oil is insoluble in water, again, because they will not mix. There is a limit to solubility. Even with things that are soluble in each other, there is a limit based on temperature, as to how much you could get to dissolve. You know, if you're sitting at a table, right, and you got those little sugar packets at a restaurant, right, you put it in your water, it'll dissolve, right? But if you go and get the Costco size thing of sugar and you got still your little cup of water, at some point, it's not going to dissolve all that sugar, right? It's just going to pile up. So there is a limit to how much you could get to dissolve at a given temperature, even if they are soluble in each other. Gases are always soluble in each other, and the idea of gases always being soluble in each other is they are flying around. So they're constantly mixing with each other. They're constantly passing each other as they're flying around, and they're always going to be soluble in one another. Some liquids will also be soluble, and again, that would be your polar and polar liquids together, or your nonpolar and nonpolar guys. And again, if you're mixing two liquids and they are soluble in each other, it will just look like this. If you're mixing two liquids and they're not soluble in each other, you will see different layers, right? Insoluble. Sometimes when people talk about liquids and liquids mixing, they talk about it being miscible, which means that they will mix and be soluble, or immiscible, which means that they will be insoluble and have different layers. But definitely put two liquids together and they don't mix, they're not soluble in each other, you'll see definitely different layers happening. But if they are, it would all just look like one solution, basically. How do we know if we put things together whether or not we will get a solid or not? We can use solubility rules to help us determine if we throw these two ions together, will we make a solid or will we not make a solid? So these are solubility rules from a solubility table. Group 1 is soluble in everything. There's no exceptions. So as soon as you see any member of group 1 in a formula, you know it's going to be soluble. And if something is soluble, those are the guys in equations that get the aqueous symbol next to them. So if something is soluble, it means it's a solution. Those are the guys that get the AQ or aqueous symbol next to it. If things are insoluble, those are the guys that get the solid symbol next to it, or the S symbol next to it. Anything that has ammonium in it, anything that has nitrate are going to be soluble in everything. There is no exceptions. Chlorides, bromides, and iodides are soluble in everything, but there are actually 3 exceptions. So all these guys are going to be aqueous, but if it's one of these 3 exceptions with chloride, bromide, or iodide, it does the opposite. It becomes insoluble. Sulfates are also soluble in everybody. It should be aqueous, but if you have one of these guys with the sulfate, it will be insoluble in this case. Now, there's also things that are typically insoluble. So if you see carbonates, You see phosphates, or you see hydroxides. These guys are typically going to make solids, except if they're hooked up with any of these guys, which are basically group 1 on the periodic table, then they will be soluble. So how does this work? If you think about a double displacement reaction or a precipitation reaction, you take a little silver nitrate, and I add a little sodium chloride to that. A little double displacement reaction, positive, negative, going to make sodium nitrate and silver chloride. We could use these solubility rules here to determine what everything's going to be. You may not be able to find both things in the table, but you should at least find one. So in this case, I see nitrate on the table. Nitrate is soluble and there is no exceptions, which means I know as soon as I see that nitrate, this guy is going to be a solution. It's going to be aqueous. Sodium is group 1 on the periodic table. Boom, that's right there. As soon as I see that, I don't have to look any further. There are no exceptions. I know that is always going to be soluble in this case. Same thing over here. I look at sodium. I don't need to go any further, but if you did, you would also see nitrate, which both tells you is going to be aqueous. I see chloride here, which is right here. It is soluble in everything except what 3 things? Silver, lead, or mercury. In this case, the chloride is actually attached to silver, which is an exception. So instead of being soluble, it's going to do the opposite. It's going to be insoluble, and you will make a white solid. You maybe did that during some chemical reactions. You get like a white solid that is formed. So this is how you can use solubility rules to determine if you put 2 ions together, would you expect a precipitate to happen or not? A lot of times used in double displacement reactions or precipitation reactions to help you decide what you would get. Question on those there. So why don't you try one here? Let's say I did this reaction. Trying to remember what I'm going to do. Yeah, let's do this one. Plus this goes to this plus this. All right, use the solubility rules here to determine is it aqueous, these guys, or solids. Again, aqueous for things that are soluble, solids for things that are insoluble. See, so again, like I said, you may not be able to find both things on the table, but you should, again, at least be able to find one of the things. So here's potassium, which is group 1 on the periodic table. That is right here. That is soluble pretty much in everything. So because it's soluble in everything, there's no exceptions. That's as far as you need to look. That is going to be aqueous. That will be a solution because it has potassium in it. Here, lead you may not find on the table, but nitrate is what we see here. And nitrate's on the table. And it also is soluble in everything. There's no exceptions. So because that has nitrate in it, I know that's also going to be a solution, which is why if you ever look at the solutions in lab, a lot of them are something nitrates, and then they're in the solution bottles because they're pretty much soluble in everything. So they'll make solutions with everything. Here we come over here, potassium is as far as we really need to look because that's group 1. If you're not convinced, you could also look at nitrate, which should still convince you that they are both going to be aqueous. Now, what about this last guy here? I is iodides, which is soluble in everything. But again, there are some exceptions, right? And is this one of the exceptions? It is. It's because it has lead with it, right? So instead of being soluble like it normally is, it will be insoluble, and this would be your yellow solid that you would actually make if you put those 2 solutions together. So you can actually pour 2 solutions together, and because they are a solution, like I talked about before, basically they're ions floating around, and those 2 ions, the lead and the iodide, will come find each other and make this yellow solid and actually come out of solution, which is why you could see the solid being formed because it's no longer floating in the solution. And essentially, it kind of came out of the solution when they come together. Any questions on that there? All right. Solubility rules, if you need them, would probably be provided for you, I think. You just need to know how to use them, I think. Yeah. All right. Then let's talk about solutions and solubility as well. We talked about the idea of like dissolves like. So as I mentioned before, pretty much we're going to get some good mixing when we got everybody using really the same type of interaction that they use with themselves. The solubility of a solute does depend on temperature. Typically at a higher temperature, you will have a larger solubility of a solid in a liquid. That is why they tell you sometimes you're trying to dissolve something, just kind of warm it up a little bit. And when you warm it up, you're doing a couple of things. Definitely when you warm it up, you're adding more energy, right? Going to get everybody moving a little bit more, even that solid, right? It's going to pick up a little energy. That's going to incorporate them and allow them to sort of dissolve out and start the dissolving process. At a lower temperature, you have a larger solubility of a gas in a liquid. So at a lower temperature, right, my gas molecule, which is my circle, will it be moving faster or slower at a lower temperature? Slower. So it's just going to kind of take us longer time in that liquid part, right, as it's trying to get out and come out of the container and come back in the container. So it's going to take a lot longer for it to get out of the liquid part because it's not moving as fast, right? The solubility of gases also depends on pressure. The higher the pressure, the larger solubility of gas. In a liquid, for example, that's known as Henry's law, also known as like the soda can example, right? When you have a soda can, right? You have a bunch of CO2 molecules, gas molecules, dissolved in the liquid part, right? Before you pop the top of your soda can, right? It's under a lot of pressure. When you pop the top, you release all that pressure. And what do you sometimes see coming out? Fizzing out. Yeah, you see that. That's basically the CO2 escaping, right? And you're able to do that because you release the pressure. You also gave it an escape point, which is really bad because when you leave your soda open for a while and you come back to it, it tastes, yeah, because all your carbon dioxide just floated away, right? And it's no more carbonated anymore. Basically, it's just a flat, syrupy water at mess at that point, right? You still drink it because you're thirsty. It happens, right? And you do that thing. But that's the idea there. Again, before we pop the top under a lot more pressure, it's going to keep that carbon dioxide in the liquid part of it and keep it all bubbly, I suppose, right? Now, there are some ways that we can classify solutions. So let's talk about that. There is a limit to how much you can get to dissolve at a given temperature. You can have a situation where you have too much solute dissolved in a solvent. That can be a situation known as a saturated solution. A saturated solution is a solution where at that given temperature, you pretty much hit the point where that's all of it's going to dissolve. No more will dissolve at that point. You've hit the maximum amount of solid that will dissolve at that particular point, sometimes referred to as the saturation point. You pretty much hit the maximum amount of solute that will dissolve in that solvent. If you decide to add more, say sugar, like my Costco example, at some point you're going to hit a saturated solution. And if you keep adding like that sugar, it's not going to dissolve. It's just going to kind of pile up on the bottom, right? The opposite of that is an unsaturated solution. An unsaturated solution, you have not hit that point of saturation yet, which means if you continue to put solid in the water, for example, it will continue to dissolve. And it will continue to dissolve with no problem because it's unsaturated. It will continue to dissolve until it hits what? Until it hits a saturated solution. So you can continue to dissolve your solute in that solvent, and it will continue to dissolve until eventually you will again, if you keep doing it, hit a saturated solution. And at that point, no more will dissolve. Any questions on that there? There's also a supersaturated solution where you have way too much dissolved in that particular solvent. The way you make a supersaturated solution is you actually dissolve stuff while you're heating it up. So as I heat it up, right, the solubility is going to increase because I'm increasing the temperature. So I could dump a bunch of solid in there and it's all going to dissolve. And after you do that, you let it cool down. When I let it cool back down from the higher temperature, what happens to solubility? It goes up or down? It goes down. Problem is at this point, you've already dissolved it. It's already in the solution or in the solvent. So what you create actually is a quite unstable solution at that point because you essentially have too much solid dissolved, but you already got it dissolved. So it's still a solution at this point. It is so unstable that if you just take a speck of whatever you dissolved in there and drop it in there, it will go, oh no, and all the solid will come out of the solution, and it will go from like a liquid state to a solid state by just dropping like the teeniest little bit in there. It's like enough to like push it over the edge, basically, because it's really unstable. Those type of solutions are also so unstable that if you're not careful enough, and I've done this on many demonstrations, and you just like tap it, it will cause everything to come out of the solution because it's that unstable without you adding anything. So you have a nice solution, you just kind of gently tap it, and you'll just see all the solid come out of the solution because you've increased the solubility by heating it, got a bunch of it to dissolve in there, then you lowered it back down by cooling it back down, and now we got a problem because now we got too much dissolved where it shouldn't be, and it recognizes that at the lower temperature, and that's why it's very, very unstable. It's a cool experiment. They used to do that a lot at schools, but they lost a lot of thermometers because they would always in those experiments tell the kids, put your thermometer in the test tube. And then when it would cool back down and become hard, they had all their test tubes, a thermometer stuck in the test tube like like a popsicle. So like, how do we get it off? Break it? No. But schools lost a lot of thermometers here in those experiments. All right. Other ways that you could classify solutions is concentrated. A concentrated solution is one that has a lot of solute dissolved in it. One of the most common units of concentration, as we'll talk about in this chapter, is molarity. Molarity is capital M. It stands for moles per liter. You might have seen it on some of your bottles where it says like 18M. I hope not, but that's pretty strong. Maybe it says 6M. So that M stands for molarity, is a concentration. The bigger the number, the stronger it is. You should be super careful. Yes, if you see a big number next to an M on a bottle. A dilute solution, which is typically what you use probably in your labs, is a solution that has a smaller amount of solute dissolved in it. Usually we take a concentrated solution and we dilute it down and use it as a dilute solution, right? And common example, right? We grab the big gulp there before you come to class, right? With your ice and drinking it, and it tastes really good. You leave it in your car, you come to class, you come back out, you give it a taste. Maybe it doesn't taste so good anymore, right? Because all the ice has, right, melted and diluted it in water, right? And not as strong as it was because now you have a lot more solvent molecules, water molecules in there. And we, again, still drink it depending on the situation, right? You're like, I don't got anything. The car's 100 degrees. I'm going to go with it. All right. Any questions on that? We're going to talk about electrolytes now and what they are, I think. We'll talk about that. Actually, we'll go here and talk about. Let's talk about electrolytes. Electrolytes are substances that will break apart into ions in water, basically, or solution, basically. And it's the presence of these ions that help it conduct electricity. Now, there's different types of electrolytes. There are strong electrolytes. Strong electrolytes will 100% break apart in solution. And you pretty much have all ions. You have none of the whole units together. So if you had a sodium chloride solution in the actual solution part, when it's actually in that solution, it will break apart into sodium ions and chloride ions. 100% of what you got going on in that solution are those ions. You have none of these guys still together. They have all just completely broken apart in ions. Because it has produced so many ions in solution and it completely breaks apart, it is able to conduct electricity really, really well. It will conduct electricity very well. The classic example is the light bulb example, like you might do in this lab. So if you take a strong electrolyte and you take a light bulb that has some electrodes to it and you stick the electrodes in it, the light bulb will come on very, very brightly. Yeah, because it has no problem conducting electricity. So it'll be very, very bright, the light bulb. Now, if you have a weak electrolyte, it will mainly stay together, but it will break apart a little into ions. So you're still conducting ions, so it's still able to conduct electricity, but nowhere near what a strong electrolyte could do, but because it will mainly stay together. So if you took something like HF, which is a weak acid, and when it's in solution, it will break apart a little bit into these ions. So you will mainly have this whole thing still together, but you will produce a little of these ions. So in that particular solution, you basically have HF floating around, but you do have a little bit of H plus and a little bit of F minus floating around in the beaker. And because it's still there with a little bit of ions floating around in the beaker, it's still able to conduct electricity. So the example with the light bulb, if you do that light bulb example, it will turn on, but it'll look kind of dull or dim, like it's dying, but it's still able to conduct a little bit of electricity in that particular case. Also, a major difference in the way the reactions are written. Strong electrolyte, one-way arrow. Yes. Weak electrolyte, two-way arrow. Yes. That is a reversible reaction, and that is how you know for sure it's a weak electrolyte. When you have a weak electrolyte, you will have that arrow that heads in both directions. And when you have that arrow that heads in both directions, there is a forward direction, which goes from reactants to products. And there's a reverse direction that goes from products back to reactants. So it goes in both directions, and that is definitely how you can recognize an equation that this is a weak electrolyte when you see that. Lastly, there is a non-electrolyte. And a non-electrolyte will dissolve in water, but no ions are created. And because it does not create any ions, you will not conduct electricity. Sugar, right? Sugar is a covalent compound, as we saw earlier, carbons, hydrogens, oxygens. If you have solid sugar, you could put that into water and it will dissolve into aqueous sugar, but it will not break apart because they are sharing electrons. So it's not going to create any ions. So you will not have any ions in that solution. You would just have a bunch of sugar molecules floating around, no positive guys, no negative guys. So it will not be able to conduct electricity. Again, if you put the light bulb in that, not going to go off. Yeah, so it will not go off in that type of situation. So a strong electrolyte, how do you recognize it? Well, you have a one-way arrow, you have some type of ionic compound on one side and ions on the other side. Strong. Weak electrolyte, how do you recognize it? Like I said before, you have something on the left-hand side, you have these two arrows, and you have some ions on the other side. And a non-electrolyte, you'll pretty much have the same thing on both sides, except that it will dissolve, but you will again not have any ions, basically. So that's the way you can recognize a non-electrolyte versus a weak electrolyte or a strong electrolyte if you look at the equations. Question on that there. By the way, is pure water a good conductor of electricity? Pure water. Pure water is a terrible conductor of electricity if it's pure water, because water is also covalently bonded, right? So there's no ions, basically. Remember, though, that the water that comes out of your shower and And house is not pure water. Yes, there are ions in it, and you will electrocute yourself if you decide to blow dry your hair in the shower, right? That's why we don't do that. I don't know why you don't do those things. Don't do those things. Nice warning on the video as well. So don't do those things. Bad idea. Or listen to the radio in the shower, I suppose, as well, unless it's waterproof, I suppose. But they actually put ions into your water to purify it, right, and clean it. So they actually insert ions into your water that comes out of your pipes. So it actually is a good conductor of electricity. By the way, we talked about sodium chloride. If I had solid sodium chloride and I stuck my little electrodes in there with my light bulb, would it go off? It would not. It would not go off because it needs to be dissolved and release those ions into solution to float around. So it would not in that particular case. Any questions on electrolytes? Yeah. Let's talk a little bit then about equivalents. Now, a lot of body fluids typically contain a mixture of several electrolytes. And an equivalent is the amount of ion that's equal to 1 mole of positive or negative charge. So how do we figure out sort of the equivalence? It's based on the actual charge. So for example, if I have sulfate, charge of sulfate is 2, yes, minus. It's actually the number here is the only important thing. We can actually come up with a conversion factor like 1 mole of sulfate will give me 2 equivalents. And the 2 comes from the charge. Now, if I had sodium and 1 mole of sodium ions, how many equivalents should I have? Charge is +1, right? So it would be 1 equivalent, yeah? Doesn't matter if it's positive, doesn't matter if it's negative. You could use those as conversion factors. So very commonly, we will use these as conversion factors to convert from really this unit here, which is molarity, which is, again, moles per liter. So, for example, if I had a 0.25 molar solution of sodium chloride, and again, this big M means that if I take that M out, it is these 2 units, and the number stays with the moles part, and it's per liter of sodium chloride. That is the same thing. And as we'll talk about when we really get into molarity later on in this chapter, I highly recommend you do that, because when people do not turn the big M into moles per liter, they forget all about the liters part. They have no idea where the liters part is. They don't even remember it's there. They just think moles and moles. That's the only thing I think about. So it's a really good idea to pull that out. We calculate molarity by taking the moles of whatever it is, the solute, divided by the total liters of solution, and that will give you your molarity. Now, if we wanted to know what this would be in, say, equivalents per liter or milli equivalents per liter, which are 2 very common units that are used sometimes for this type of stuff, electrolytes, we could do that because we can figure out our relationship here. First off, the relationship when I look at something like sodium chloride and it breaks apart into sodium ion and chloride ion. If I know the molarity of this guy as 0.25 molar, the relationship, just like stoichiometry here, for every 1 mole of this, how many moles of sodium ions do I get? 1. It's a 1-to-1 relationship, which means if I'm interested in just the molarity of the sodium ions, you would take 1 times 0.25 molar, and it would be 0.25 molar sodium ions. What would chloride be in this case? It is a 1-to-1 relationship, right? And that means that if I was interested in just the chloride ions, I would take 1 times 0.25 molar, and that would give me 0.25 molar for the chloride ions. This is how you can relate molarity into the individual ions. It's basically done by kind of mole-to-mole relationship. For example, though, if I had, say, calcium chloride here, right? And we have the same 0.25 molar. When this breaks apart, I get a calcium ion, right? and how many chloride ions? 2. Yeah. That affects the concentration. And in this case, it's a 1-to-1 relationship between these two guys, which means I would take 1 times 0.25 molar, and that would get me 0.25 molar calcium ions. But what is the relationship between this guy and the chloride? It is a 1 to, you get twice as much, right? You get a 2-for-1 special on that when it goes for a swim. Get twice the chloride than you do the calcium in this case, right? So you got to multiply the concentration by 2. And that means that the concentration for chloride would be 0.5 molar for chloride. And again, it's twice as concentrated. It's basically what that number means, right? I have 0.25 molarity of calcium floating around. I got twice as much molarity, right, of chloride floating around, because again, it's a 2-for-1 deal on that. You got twice as much chloride go into the pool as you do calcium in this particular case. Any questions on that relationship there? Yeah. What's that? Yeah, so it is, you could leave it one of two ways. You can leave it as molarity, big M, or you can turn that big M into moles per liter. It's perfect fine. And you wouldn't leave it as M over L. You would want to write moles per liter. So how does this help us with like equivalents per liter and stuff like that? Let us do this one first, and then we'll do this one here next. So we'll start with this one. And let's say we did have this sodium chloride, which we now know has 0.25, and I'm going to turn it into those units, moles per liter of sodium ions. And again, that moles per liter is the same thing as the big M. And it also has 0.25 moles per liter of chloride ions. And now in this case, we want to turn those into equivalents per liter and milli equivalents per liter, right? First off, which unit I don't have to play with in this one? Which unit is good to go? The liters, right? Liters are on the bottom of my original number, and liters are on the bottom of what I want to end up with, right? So I don't even have to do anything with that part, right? The only part that I have to change is the moles on top to equivalents, right? So that is what we're going to use. We saw earlier that if I had 1 mole of sodium ions, that would give me 1 equivalent, right? And again, that is from the charge. So if I take my sodium, 0.25 moles per liter of sodium, and I use this as a conversion factor, I would want moles of sodium on the bottom, ions, and 1 equivalent on top. The moles of sodium will cancel. That will give me 0.25 equivalents per liter of sodium. Yeah. Now, if I want milli equivalents, right? So the way you can remember this is like this. How many milliliters are there in a liter? Yeah, there's 1,000 milliliters in a liter. So how many milli equivalents would there be in an equivalent? 1,000 milli equivalents and 1 equivalent, right? It is the milli conversion. It's the same conversion, right? So we could use that. This would be one of the answers, by the way. We could also use that as a conversion factor, and in 1 equivalent, there would be 1,000 milli equivalents. Those will cancel, and you'll end up with 0.25 times 1,000. Move that decimal 3 places, probably. Or 3 places, but I hit 1,000 and not 100. And I did it again, but we'll go with 250 milli equivalents per liter of sodium ions. Any questions on that calculation? So it's really equivalence, just a conversion factor to convert a concentration unit from one concentration to another. We could do the exact same thing for chloride. So if we do the exact same thing for the chloride ions that are floating around in the solution, for every 1 mole of chloride ions, how many equivalents? 1, right? Based on the charge, -1, 1 is the number we're looking for. And we could do the same type of conversion. We would have 1 mole of chloride ions, 1 equivalent. Moles of chloride will cancel. Will leave us 0.25 equivalents per liter of chloride. And we could also do the same conversion into milliequivalents, 1,000 milliequivalents per equivalent. And that will get me 250 milliequivalents per liter of chloride ion. Yeah. Any question on that calculation? Now let's take a look at the calcium chloride to show you how it's a little bit different in terms of maybe what we end up with to finish it up on here. So we also had, we're going to look at this guy now, our 0.25 of our calcium chloride. So in that case, we had 0.25 moles per liter of calcium ions in that solution. We also had, remember, because it's twice as concentrated, 0.5 moles per liter of chloride ions in that solution. We again want to do the same thing. We want to figure out what those concentrations would be in equivalents per liter or milliequivalents per liter. So we'll start with the calcium. For 1 mole of calcium ions, how many equivalents will I have? It is 2. It's just the number, right? So it would be 2 equivalents. So if we do our first calculation here, 0.25 moles per liter of calcium, 1 mole of calcium ions gives us 2 equivalents. The moles of calcium will cancel. We'll leave us with 0.5 equivalents per liter of calcium, which would be one of our answers. We also could do our milli conversion on this guy like we did on the previous problem. 1,000 milliequivalents in an equivalent will give us 500 milliequivalents per liter of calcium ions. Yeah. Question on that one there. Now, again, we're going to do the same thing for the negative ion in the solution. So we'll go with 0.5 moles per liter of chloride ions. And 1 mole of chloride ions, how many equivalents? 1 equivalent. So again, using that as our conversion factor, 1 equivalent per 1 mole of chloride. Moles of chloride cancel, gives us 0.5 equivalents per liter of chloride. Also, again, doing our milli conversion there with our 1,000 per equivalent. Gives us 500 milliequivalents per liter of chloride ions. So you could calculate the ions that are floating around in an electrolyte solution like an IV bag. And you could calculate the concentration equivalents per liter or milliequivalents per liter. The question I asked here to you ended on, I think, is this question. Is the concentration in equivalents per liter or milliequivalents per liter for each ion in this solution, is it the same or different? The calcium is 0.5 equivalents per liter. The chloride is same. 500 milliequivalents per liter for the calcium, 500 for the chloride. Same thing if we look on the previous example. For the sodium, 0.25 equivalents per liter. The chloride, 0.25 equivalents per liter. This is based on the charge, right? And what do we do when we put an ionic compound together that has a positive, negative charge? We make sure it equals 0. It balances each other out. So these concentrations are related to the charge of the ions that are in the solution. And because an ionic compound should have an overall charge of 0, always when you calculate those concentrations in equivalents per liter or milliequivalents per liter for a solution that contains a positive, negative ion, they should always end up the same concentrations, the exact same number when you do equivalents per liter and milliequivalents per liter, because their charges should be balanced out, which is how we put it together in an ionic compound. Any questions on that there? And equivalents are essentially a conversion factor that we use a lot of times with electrolyte solutions. It is based on the charge of the ion that's present. And it doesn't matter really if it's a positive ion or if it is a negative ion. It is actually just the number here that's important. So we could come up with a conversion factor that 1 mole of sulfate gives you 2 equivalents. And the 2 is basically from the charge. And the same thing here, if we had 1 mole of calcium, that would also be 2 equivalents in this case because of the charge. So a lot of times we may convert from molarity like we did last time there, moles per liter, into something like equivalents per liter or milliequivalents per liter, which is commonly used sometimes for electrolytes. And as we saw, for example, I think we might have looked, I don't remember which one we looked at, but if we looked at something where there's sodium ions and maybe there's sulfate ions, and when you calculate the equivalents per liter for the sodium and the sulfate, and also the milliequivalents per liter of the sulfate and the sodium, what you'll see is in those couple examples that we did, for each the positive ion and the negative ion, they will end up the same concentration of equivalents per liter because it's based off the charge. And when we put an ionic compound together, we make sure the overall charge is 0. And that means in terms of the charge sort of concentration, we actually have the same sort of charge concentration in that solution. And they should always be that way. If you have a cation and anion in an electrolyte solution and you calculate either of these guys here for both of them, they should end up being the same for both. Because it should be a balanced ionic compound of positive and negative charges in there. Any questions on any of that stuff there we talked about last time? Okay, then we're going to continue on, and we're going to talk about now concentration units for solutions. So the first type of concentration unit we're going to talk about is mass percent. It is sometimes abbreviated percent mass to mass, and sometimes referred to as mass to mass percent. To calculate the mass percent of a solution, you would take the mass of the solute divided by the mass of the solution, and you would times it by 100%. The important part of this type of calculation is actually the bottom. And remember that the bottom is made up of 2 things. A solution is a solute plus the solvent. So you definitely want to make sure when you're doing that calculation that you do get both of those numbers. The reason why it's important to do so, especially with mass percent, is I would say it's super common in those type of problems that they will break those numbers up and give you the mass of the solute separate from the mass of the solvent. And it's a very common mistake that people make, which is they just end up dividing by the mass of the solvent rather than the entire solution together. So you definitely want to make sure that you have the mass of the entire solution. Now, for example, if I had a mass percent given to me, like if I had one that said 4.5% by mass sodium chloride solution, I can turn that percentage into a usable conversion factor, which sometimes is easier to do than plug and chug into the equation. And the way I would do that is like normal percentage rules, which is if you have a percentage and you want to kind of turn it into a usable type of number, we usually assume that we have 100 of something, right? And what that does is it keeps the percentage the same number, so you don't have to change numbers or anything like that. So if we take that assumption, we could actually turn this into a usable conversion factor. And what that would mean is that we have 4.5 grams of sodium chloride in 100 grams of solution. So that is a basic kind of conversion factor that we could get from that value or that concentration that we could use. And because it is a conversion factor, we could also flip it around the other way and put the 100 grams of solution up on top and the 4.50 grams of sodium chloride on the bottom. So sometimes when you're doing problems and you are given the mass percent, sometimes it's just as easier to do it more like a dimensional analysis conversion problem and turn that percentage into a conversion factor and just kind of use it like that. Any questions on that there? All right, why don't you try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent of calcium chloride in the solution. So let's see what you come up with here. Okay, so let's take a look here. Obviously, here we're looking for percent mass to mass. So that is our formula we saw, which is the mass of the solute divided by the mass of the solution times 100%. In this case, we have 2.5 grams of calcium chloride. That is the smaller part of the solution. That is the solute. Water here is the solvent, as it works good for a ionic compound. So we have our mass of solute, which is 2.5 grams. We have our mass of our solution that we need to calculate. Remember that the mass of the solution is the solute plus the solvent. So here we would want to take 2.5 grams and add it to 50 grams. And that is going to give us the mass of the solution and not just the solvent. And we'll have 52.5 grams of solution. Again, that is what needs to go on the bottom, not just the solvent. And if we put that in there, that'll give us 2.5 grams divided by 52.5 grams times 100%. That is 2.5 divided by 52.5 times it by 100%. Going to give us 4.76%. You could label this M/M, which stands for mass to mass percent. You want to get really fancy with it, calcium chloride, which is what we're talking about in this particular case. Any questions on that calculation? Again, getting the mass of the solution is really important. It's very, very common. These have problems that they do separate out those values. And again, very common that people just divide by the solvent rather than adding together and getting the solution. Any questions on that there? All right, then let's try another one. Concentrated hydrochloric acid solution contains 37.2% by mass. What is the mass of hydrochloric acid contained in 35.5 grams of the solution? So let's see what you end up with here. Bless you. Bless you. Okay, so let's take a look at this one here. We have the mass percent given to us, which is 37.2%. We're looking for the mass of the solute here, which is our HCl. And that is what we're looking for. By the way, I know that is the solute, and that's what I'm looking for because we're looking for the mass of the HCl. Remember that the name of the solution is the solute. So if you're looking for HCl, then you're looking for the solute in this case. That means that the other number, like it says there, is our solution, which is 35.5 grams. Now, clearly, you can plug and chug into this equation here if you like and solve for what you are missing, which in this case would be the top there. That would be what you're missing. You have pretty much that, and obviously you have that. The other approach you could take is you can take more dimensional analysis approach. So since it is 37.2% by mass HCl, what that means is there are 37.2 grams of HCl in 100 grams of solution. Or you could flip it around, 100 grams of solution is 37.2 grams of HCl. So if you don't want to remember the formula, you could just take a more dimensional analysis sort of approach to it, which is, I know I have 35.5 grams of solution. Remember that opposites cancel, which means I do need solution on the bottom, which would be that guy right there. 37.2 grams of HCl divided by 100 grams of solution. The grams of solution will cancel, And we'll add 35.5 times 37.2 divided by 100. Going to give us 13.2 grams of HCl. By the way, that is the exact same math you would do if you just plugged it into the equation as well. But you can't remember the equation. Again, you could turn that conversion factor or turn that percentage into a conversion factor and just kind of take it like getting rid of the units you don't want to keep the units that you do want. Any questions on that? And again, you basically, if you plugged it into the equation, you would go 37.2% equals my grams of HCl divided by my 35.5 grams times 100%. You would divide the 100 to the other side, which is what it is right there, and you would multiply the 35.5 to the other side, which is what it is right there. So again, it's same math. If you plug it in or do more of a conversion factor way. Any questions on that there?